Let's consider another carboxylic acid derivative, and this actually is going to be one of the most important ones that we'll see, and it's one of the most common ones. And this is the ester. It's a functional group that's shown here. For an ester, so we have R, C double bond O, O, R, which could be R prime. It could be a different alkyl group. And these esters are of interest because they're really, as I wrote there, the most widespread naturally occurring compounds. We find esters in all sorts of different scenarios, very important in terms of biology as well. And a lot of them are actually nice smelling compounds. So back when we used to be able to do things in the outside world, in the lab, a lot of the times people would you'd make esters in an organic chemistry lab, which is nice because you can make things that smell good, like this isopentyl acetate is something that gives bananas the smell of the banana. I remember back when I took organic chemistry eons ago, I made something that had a smell of cherries in the organic lab. And I got a little bit of it on my calculator, I remember. I don't know, I had my calculator out, but for some reason it did. And but it was good in a way that my calculator smelled like cherries for more than a year. Probably toxic, but at least it smells good. Okay, but we're going to see a wide variety of these esters. And so we want to think about how to make esters and then what to do with them. So a couple of different ways to make them, and I'm going to use this as a review for the most part, is we could take a carboxylic acid and in a classic SN2 reaction. Let's go ahead and deprotonate this. Thanks for the laughter. I appreciate that. And so we could go ahead and deprotonate this, and then in an SN2 reaction, attack this methyl iodide, say to make this methyl ester here. This has a limitation though, because it is an SN2 reaction, so it's methyl or primary alkyl halides. So if you want to make something like this relatively simple methyl ester, this is a great way to do it. But let's say you had a much more complicated group here with a bunch of substituents on it. Not good for SN2. I think for the interest of time, we won't go through this particular reaction, but you can use this compound diazomethane with a carboxylic acid. And you can use this also to introduce some methyl ester. So the methyl group is coming here from this carbon of the diazomethane, and you release nitrogen. If you're interested, I think that one's in the textbook, and so you can take a look at that mechanism. There's two more ways based on things that we've already seen, is we could take our acyl chloride and react this with an alcohol. So that if I were to scroll above, we would have seen that, and we generated an ester. So some alcohol, R prime here, shown as R prime is our product, and we can use pyridine as a base. And so that was one reaction we saw with the acyl chloride. Just a few minutes ago, with Tylenol, we reacted acetic anhydride with the amine. However, instead of the amine, the nitrogen-containing species, let's use an alcohol. And we could have the alcohol attack one of these two carbons, tetrahedral intermediate, kick this acetate out, which would be this species here. Acetic acid is the protonated form. And we're going to end up with an ester. So whatever this R group here is, will end up being the R group of the ester. So that's another way of making them. However, one of the most common ways and a very useful reaction of making esters here is what's known as the Fischer esterification. And this one allows us to take a carboxylic acid and an alcohol in the presence of acid. And you can see we can use this to make the ester. So it's a very mild condition. You can just have a little bit of acid. You can buy a wide variety of carboxylic acids. A wide variety of alcohols are available. We can use this to make all sorts of different esters. So I think it's worth it to go through thinking about how this reaction might actually occur, because it's a nice review of a lot of things that we've already seen. And I don't know why I didn't leave much space here. So let's think about the potential mechanism for this reaction. We were talking the other day about adding pages and when to do that. It should be neater that way. Is it this one? No, this one. I'm trying to remember what we did. The first one? Brian's way ahead of me. Oh, this one. No? Oh, the 3 dots. Okay. Paper. No. Click the 3 dots. And where the page is at. Oh, this one. Got it. Thanks. Excellent. Thanks, Brian. I can learn. Okay. Let's think about a mechanism for this reaction. We'll use the whole page now that we have it here. And let's get rid of the R group and just make it a methyl. And let's get rid of R prime. Just make that methanol. Okay. Excellent. Thanks again, Brian. Otherwise, we'd be doing this for a long time. Now, this reaction here, we have a carboxylic acid. So unlike our acyl chloride earlier, where we had this chlorine pulling electron density away, not really donating by resonance and making this carbon very electrophilic, now we're kind of back in the world of our aldehydes and ketones, because the oxygen can actually donate electron density here through resonance. And we have our weak nucleophile. So if we were to just mix these two together, if we just take acetic acid in the presence of methanol, not much is going to happen. So this is why we want to have just a bit of acid around. So this particular case, we'll just put H+, H3O+, we'll have water, just a little bit of sulfuric acid here. What we're going to do, is going back to the days here of aldehydes and ketones, is let's turn this species into a much more electrophilic species by protonating it. So we can have something like this. Now, let's have methanol as our weak nucleophile. Attack. Tetrahedral intermediate. We have OH here. OH here. Oh, sorry. There it is. And now we have this intermediate. Now what we need to do is we're going to carry out a couple of proton transfer steps. So we're going to deprotonate this species to get rid of this get rid of this positive formal charge. So let's put it down here. So we have something like this. We regenerated our hydronium ion. Now what we want to do is turn one of these two bad leaving groups into a good leaving group. And we can do this by acid. So we're going to protonate this. I'll expand this so we can see the 2 protons. And then we have O CH3 here. Now what we're going to do is we're going to kick out our good leaving group. Reforming our carbonyl group. Plus water. And now to get to our final ester, all we have to do is remove that proton. And we have this species here. So overall, we've gone from a carboxylic acid plus an alcohol, and we formed an ester. So this is the Fischer esterification. A very useful reaction, as I mentioned, because we can get a wide variety of carboxylic acids and alcohols. Just with a little bit of acid, we can form the ester. So here on the bottom right, Crystal asked about which hydroxyl does it matter which one we protonate? And here it does not. These are both going to generate the same thing. So you could protonate this one on the top just as well, and then have these electrons on this oxygen come in and kick that group out. One of the things to note here is that this reaction actually, it is in equilibrium. Overall. And so all of these steps are reversible, kind of like with the acetal formation that we've seen earlier. And we'll see this again. So this one, actually, you can go backwards. So we can take an ester, turn it into carboxylic acid, because all the reactions are reversible. And this one, you can actually quite nicely change the direction of the reaction, because notice here, when we kicked out either one of these, since it doesn't matter which one we protonate, notice what we're doing is we're losing water in the reaction. So I wanted to highlight here. So water is being released in the reaction, which means then if we want to drive the reaction forward, we can keep taking out the water of the reaction. So we can dry the reaction, remove the water. However, if we want to push the reaction the other way, we can add water back into the reaction. So it goes back to Le Chatelier's principle from Gen Chem. So it's a nice way of being able to push the reaction in one direction over the other. One other point is, and this is kind of following on Crystal's question, is when you have the two hydroxyl groups here, it doesn't matter which one you protonate. However, when you get to this compound, this one here, if we protonated this ether species, the OCH3, then you would end up just going back to in the reverse here as well. So it does matter which one. You don't want to protonate this species if you're going in the forward direction.